Hello, everybody, and welcome to today's webinar with Dr. Benjamin Zand. My name is Nick Rendell with Technical Toolboxes, and we'll get going here in just a minute. A couple housekeeping items before we do. There's going to be a lot of very good, very dense content throughout this webinar. So if you do have questions on what Dr. Zand is covering, there is a chat box on the right-hand side of your webinar interface. Feel free to add your question to that chat box, and we will do our best to answer all questions at the end. So with that, I'll hand it over to Dr. Zand. Thank you very much.
Yes, thank you. Thanks everyone for attending this short course. So the objective of the course is to basically talk a little bit about the CEPA model and also potential improvements that we are planning to make in near future. So as you probably know, CEPA is a surface loading stress analysis tool that many pipeline companies use when they have a crossing, either crossing or other type of surface loading, such as a stockpile of material or an embankment or something like that over a buried pipeline. So currently, Technical Toolboxes has a number of different tools for surface loading analysis, and which includes the older version of the model, which is known as the Battelle model, which is based on Spangler-Iowa equation, and also the newer model that's known as the CEPA model. So let me start by quickly reviewing the CEPA model first. So the CEPA model, like I said before, is based on a model that's known as the Spangler-Iowa equation or model, which was originally developed by Marston and his student Spangler in Iowa State University. Then later on, that equation was modified multiple times, which I'm not going to go through details. The last or the latest official update of the equation, or major update, I should say, was completed by Dave Worman. Back then, he was with Kiefner and Associates. I think it was 2007 when that paper was published. And then later on, there was a PRCI project, actually two projects, in which the CEPA model, the predictions of the CEPA model were compared against some experimental data from field measurement. So here are some of the papers in case you are interested to dive into the background, the theoretical background of the CEPA model. So the objective of a surface loading stress analysis. The objective is to make sure that the structural integrity of the pipeline is not going to be affected by the added load from surface loading, which means that the stresses in the pipe, in the buried pipe, should be kept within the allowable limits to avoid yielding of the pipe. And the CEPA model is basically used mainly for steel pipes. There are similar models for plastic pipe and also for concrete water pipes that are very similar in terms of the equations that are used. But the CEPA is just a steel pipe, right? So we are going to assume that this is just a carbon steel API 5L grade carbon steel or similar material. There are also a number of other assumptions. For example, when we do all these calculations and when we talk about the allowable limits, we are assuming that the pipeline and the girth welds are in good conditions, that the pipeline doesn't have any defects, such as metal loss or dent or similar features that are considered defect. If there are such features in a pipe, then it's recommended to perform a fitness for service in addition to a surface loading analysis. So again, the way it works is that you perform your normal fitness for service analysis to get an allowable stress limit for whatever feature you have, like let's say a metal loss. And then you can perform your CEPA analysis and calculate the stresses and compare that against the stress that you got or the allowable limit that you got from your fitness for service. So the CEPA model basically accounts for the surface loading induced stress in a pipe. It also accounts for operating stresses in the pipe, which includes thermal expansion or contraction of the pipe, and also the effect of the internal pressure, the Barlow equation. The surface loading model also considers or includes the overburden or the dead weight of the soil that's over the pipe, right? So these are the forces that are included in the model. If you have any other forces that acts on a pipe, such as ground settlement or other outside forces, then the CEPA calculator does not include them. So it's up to the engineer who does the analysis to account for them. And also, when you use CEPA model from Technical Toolboxes or from any other source, it's also important to understand both the model and the theoretical background, potential restrictions that the model might have, and also to understand details of your encroachment problem, right? Such as your cover depth, what type of soil, backfill soil you have around your pipeline. Naturally, you need to know that the characteristics of your pipeline, such as diameter, wall thickness, etc. And then some additional details, such as the type of the vehicles that are going to cross the pipeline, the total weight of those vehicles, approximate speed of those vehicles when they cross the pipe, the condition of the pavement, it's asphalt concrete or flexible concrete, or is it just gravel road, things like that. Some information about the tire pressure preferably and the angle of the crossing. So the existing CEPA tool does have some ways for the analyst to account for the angle of the crossing. More specifically, there is a module that is the load matrix analysis tool, which if you use that, you can actually introduce a load or a load matrix that makes some angle with the pipe. Usually, when we do this type of analysis, typically we assume that it's a 90-degree crossing, right? So the vehicle crosses the pipeline at the right angle. And if you deviate a little bit from the right angle, you can still use the 90-degree assumption. But when your angle, the angle between the road or the vehicle and the pipeline is less than 45 degrees, then it is necessary to account for that angle, especially if the load is a long load. So we are going to talk about it a little bit more. For now, let's pass. For a typical surface loading analysis, we perform a couple of stress checks. It's the circumferential stress, the longitudinal stress, and then the combined stress, which is the combination of circumferential and longitudinal stress. And these are the checks that the CEPA model actually makes for you. So here, when we talk about the additive circumferential stress, what we are referring to is the sum of the surface loading induced circumferential stress and the Barlow stress from the pipe internal pressure, right? And one thing to note here is that the limits that ASME B31, 4, and 8, and also the Canadian standard provide for the surface loading analysis is actually more than 72%, right? So your circumferential stress is not necessarily limited to 72%. And if you wonder why we can allow stresses to exceed 72%, without going too much into detail, I just need to point out that the surface loading induced stresses are basically local bending stress. So that's the distinction between the membrane stress in a thin structure like a pipe versus through thickness bending. The limits that we use for through thickness bending could be higher than 72% in the circumferential direction, and that is basically something that the standards account for when they tell you you can use 90% or something higher than 72%. So for the additive longitudinal stress, the components that contribute to additive longitudinal stress, they include the internal pressure, because when you have a buried pipe that is longitudinally restrained, internal pressure creates some tensile stress in the longitudinal direction. In addition to that, we have the thermal stresses from changes in the temperature, operating temperature of the pipe. Then we have the surface loading induced stresses in the longitudinal direction. And that has several different components, the longitudinal stress from the surface loading induced. There is a uniform longitudinal stress from the overburden pressure that acts on the pipe. Then we have a global bending stress in the pipe. That's because under the weight of the vehicle, the ground tends to settle a little bit. It's an elastic settlement, right? After the vehicle passes, it goes back, bounces back. But that small settlement can cause bending stress in the pipe. And in addition to those, we also have a local bending because the pipeline under the weight of the vehicle, it gets ovalized. And that ovalization creates a bending stress in both circumferential and longitudinal direction. So those are the stresses. And then once we calculate those components, longitudinal and circumferential, and then add them together to get the total, then we can combine them to get the combined circumferential stress. And these are things that CEPA model basically does. Or if you use the CEPA tool, it does it automatically. So here, let's quickly look at some of the stresses that we have. The Barlow stress is the easy one. You know, the Barlow stress is calculated as pressure times the pipe diameter divided by twice the wall thickness, right? Internal pressure also creates, like I said, a longitudinal stress when the pipe is buried. The reason for that is because when you pressurize the pipe, it expands in the circumferential direction, right? Because of the internal pressure. But steel's carbon steel has a Poisson ratio of about 0.3, which means that when the pipe expands circumferentially, it wants to shrink in the longitudinal direction because of the Poisson ratio effect. But when the pipe is buried, the soil friction between the friction between the pipe and the soil prevents that type of movement. The pipe cannot shrink or expand longitudinally. So for that reason, a tensile stress gets developed in the longitudinal direction. So that's a part of the operating stress in the pipe. For the same reason, when you have a straight pipe that is restrained longitudinally and you change the temperature in the pipe, for the same reason, a stress develops in the pipe, which could be tensile or it could be compressive, depending on change. If the temperature is up, the pipe wants to expand, but the soil friction prevents that. So what happens is that you get a compressive stress in the pipe, and vice versa. When the temperature goes down, you get a tensile stress in the pipe. All right. So those are the operating stresses. Then when it gets to surface loading, we have two types of stress. We have a soil overburden, which is shown here. It's basically the weight of the soil that acts on the pipe, which tends to ovalize the pipe. Okay. So in the CEPA model, in the existing model, the method that is used to account for the overburden pressure is known as the prism load. It's basically the weight of this rectangle that you see in the picture, right? So it's simple. It assumes that this rectangle is just pressing on the pipe, okay? And then there is also a surface loading that is known as the traffic load or live load, which is the weight of the vehicles that cross the pipe, okay? Which can also cause fatigue cycles. If your crossing is, let's say, a highway crossing, which can actually have many trucks, thousands of trucks per day, then those cycles of trucks crossing the pipe, it can actually cause fatigue, which is one of the things that the CEPA model checks for. If you look at the stress check section in the result, it tells you whether your fatigue cycles are acceptable or not, right? So these are things that, again, the existing CEPA model does. And if you like to see the equation, these are the equations that are used to calculate the additive, circumferential, and longitudinal stress. So the first part, let's start with the hoop stress or circumferential, the first two equations. Here, P is the internal pressure, right? So this is basically the Barlow equation, which is P times D divided by 2 times T. And there is a high pressure and a low pressure because the pipeline can operate at different pressures, right? So when we do the calculations, we usually need to account for like a high pressure and a low pressure, which is usually 0, right? So we do both. Usually the high pressure creates the highest equivalent stress or the combined stress, right? So the highest combined stress is usually when you use the highest pressure in the pipe. And then when you use a low pressure or 0 pressure, it's usually the fatigue cycles that become the maximum value. The reason for that is because the pipe internal pressure has a stiffening effect. So a pressurized pipe is less sensitive to surface loading than an unpressurized pipe because of the stiffening effect of the internal pressure. Then the stress component that we have here, I called it soil. This is the stress that comes from the overburden soil pressure, right? So again, going back to the figure that I had on the previous slide, the weight of this rectangle can be calculated easily. It's the height or the burial depth times the unit weight of the soil. But when you have that pressure acting on the pipe, it tends to ovalize the pipe, and that creates a circumferential stress, which is calculated from the CEPA equation. So that's why here I have in the subscript, it says CEPA, because we use the CEPA equation to calculate that, right? And then the last term in the two equations is the live stress. This is the stress that comes from traffic load. And again, we use the CEPA formula to calculate that. So we still have that CEPA subscript. The difference between the second and the third components here is that the second one is basically doesn't change. Whereas the third component, it changes. It's a cyclic stress which can cause fatigue. That's why we separate them in the CEPA model. And then for the longitudinal stress, similarly, we have the component from the Barlow equation because of the internal pressure. So that's the first one. The second one that you see is related to thermal expansion or contraction of the pipe. It's basically thermal load. This term here that you see is basically, it accounts for the effect of the soil overburden, because soil overburden can also cause a longitudinal stress, right? So which is basically the Poisson's ratio times this. So you see, if you look, the third component in these equations is the same as Poisson ratio times the second component in these equations. And then the last two are surface loading induced stresses. These are basically the live stresses, or the stress that can cause fatigue on the girth welds, which has a global and a local component in both cases. All right, so these are the stresses. And again, if you look at the pipeline in the circumferential direction, when it gets ovalized, you get a through thickness bending. So to show what I mean by through thickness bending, I actually put this image here, where it says, which over here, so this is the pipe that is ovalized. It's exaggerated, it's not going to be that much. But it shows schematically what we mean by a pipe that's ovalized. And when that happens, we get through thickness bending. Through thickness bending means if you look at the wall thickness of the pipe, on one side you have compression, on the other side you have tension. For example, at 12 o'clock position, on the outer surface you have compression, on the inner surface you have tension. But then the reverse is true at the 3 o'clock and 9 o'clock positions. You have tension on the outer surface and compression on the inner surface. So those stresses, they change depending on where along the circumference you are. This is the nature of through thickness stress, through thickness bending. And it's also different than the Barlow stress, which is uniform through the thickness. Now, on the longitudinal direction, I talked about global bending. So this image over here, again, schematically, shows the global bending. What I mean by that, when there's a vehicle on the pipe, the soil under the pipe tends to settle a little bit under the weight, and that causes bending in the pipe, which is another stress that CEPA accounts for, right? So that's this component. When I say sigma bending global, that's this stress that you can see here. All right, so I just need a minute to check and see if there is any questions.
Dr. Zand, there are some questions.
Yeah, I noticed. So I think maybe it's better to, I'm trying to think. Let's take a few minutes to address some of them. And then maybe for the other questions, we have to wait until after I finish.
Okay. Would you like me to start reading them out then?
Yeah. Let's go through them. Yeah.
Okay.
I think some of questions actually are not for me, so go ahead.
Yeah, I guess the question we get from everyone every webinar is, will you get a recording of this presentation? The answer is yes, but the beauty here is in the live Q&A that we can get. All right, first question: can the CEPA model be used for aluminum pipelines?
Technically, yes. If you use the correct parameters, the Young modulus of aluminum and the Poisson ratio of aluminum and the thermal expansion coefficient, you can use it. Yeah.
Okay.
But you got to make sure that you input those parameters to represent aluminum. So what's
next? We have, what is the basis for the acceptable combined stress limits for CEPA and PTT? Is there a reference for these default acceptable limits?
The default acceptable limit for combined stress is usually 90% SMICE. And the basis for that is to avoid yielding, right? We don't want to go above yielding, so obviously it has to be less than 100% SMICE. And we also need some safety margin. So, you know, that's where the 90% came from.
Okay, kind of a similar question. Can you tell us the specific reference or standard for Canadian and ASC limits of 72% and 90% SMICE combined stress?
Yes, the American standards are ASME B31, 4, and 8. And there is a section under design that tells you what is the maximum acceptable combined stress. So the combined stress that's used in ASME B31, 4, or 8 is the von Mises stress. All right. Now, in Canadian standard, the stress that's used is the Tresca stress, which is basically the shear, maximum shear, or the difference between the hoop stress and the longitudinal stress. But again, for surface loading, that stress is limited to 90% SMICE. I can't remember the section numbers to, you know, to specify that. But if you have a document that's searchable, like a PDF that you can search for keywords such as surface loading or crossing, and you probably will find it in the standard.
Okay.
All right, so
a couple more. What effect does depth of cover on the stress on pipe and in case of soil type on pipe undergoing the CPAP?
all right. Sorry, before continuing, there is a comment here that says we lost audio.
Yeah, that was.
Are you aware of any issue or?
It was out for like maybe 90 seconds, but it's.
Oh, okay. So we are good now. All right.
Yep. Would you like me to repeat the last question?
No. So the effect of the cover depth. So let me go back a couple of slides. Okay, here. When you increase the cover depth, what happens is that your soil overburden stress on the pipe increases naturally, right? But then the cover depth also has a protecting effect on the pipe. The higher the cover depth, the lower the effect of the vehicle on the pipeline. And you know, balance between them depends on several factors, including the weight of the vehicle, the unit weight of the soil, and burial depth. To some extent, we can, when you have a surface loading problem, if you run your analysis and it fails, one of the options that you have is to simply increase your cover depth by adding to the soil cover, right? But to some extent, it can help. But beyond a certain depth, the cover depth itself, the self weight of the soil can start to cause problems. So now the soil type here again matters, because if you have a stronger soil is going to reduce, basically increase your E prime value, which is one of the parameters that is used in the CEPA. And when you have a higher E prime value, it's called the modulus of soil reaction. When modulus of soil reaction is higher, your live stress goes down.
Okay. Maybe the last question for now, and then we can regroup at the end with the others. So on slide 10, why is it that the soil and CEPA live are subtracted from the minimum stress portion?
Oh, yeah, good question. Because here, when you see it's subtracted, because we are trying to calculate the minimum circumferential stress. So what it is that if the pipeline is under a very low pressure, or let's say it's under zero pressure, you could get compression in the pipe, right? So what's the maximum amount of compression? To calculate that, we have to use these values with a negative sign in the equation, because compressive stress, conventionally has a negative sign. And again, if you're wondering why it gets compressive, again, go back to this picture that I have here. You know, at some locations along the circumference, if the pipeline is not pressurized, you get compression. And the same is true about the longitudinal stress. Move topics that we have. So here I talked about the cover depth, the dead weight of the soil, the weight of the vehicles. Basically, these are the parameters that you need for a surface loading analysis, which I think I talked about all of them. And again, to go a little bit more into details, the overburden pressure when we are using US customary units can be calculated from this equation, right? So the pressure that acts on the top half of the pipe from the soil overburden is equal to the unit weight of the soil times H divided by 144. Here, 144 is for unit conversion. If you pay attention to the units down here, you see that there is an inconsistency in the units, so that the 144 accounts for that. So this is the soil overburden. Then when it gets to the vehicle load or vehicular load on the pipe, the CEPA model uses Buzinski's equation. That again, you can see it here. This is the Buzinski equation. Here we have a point load on the ground surface, right? When it gets to some depth, point A here is my measurement point, is where the pipeline is located. This is the wheel load, this W. So how much vertical pressure we get here? This is the function that gives you the answer. It's 3 times W divided by 2 times pi times 12 H squared. Again, 12 here is for unit conversion. Times 1 plus R over H squared. And there is another exponent here, 2.5, right? So this is the Buzinski equation. And this is used in the CEPA model to calculate the soil pressure from the vehicles. So the good thing with the Buzinski equation is when you have a load matrix instead of one single load, you can still use the Buzinski equation for each single point load and then add them together or add their effects together. For example, when you have a bulldozer, you can model your bulldozer, the tracks, as a set or a matrix of point loads that act at different locations. So the way the load matrix looks like is you have a point load, right? Then you have an X coordinate and a Y coordinate. And the collection of those X and Y coordinates plus a point load gives you or provides the footprint of the vehicle, introduces that footprint to the program. This is basically the load matrix option in the CEPA tool. This is the global bending that I talked about, and here I have the equation that is used for that global bending calculations. This equation is based on beam on elastic foundation theory, and here I have a reference in case you're interested to read more about it. And the global bending in the longitudinal direction. If I go back to my equations, I'm talking about this last component here. That component is calculated from this equation. So here nu is the Poisson ratio and sigma h CEPA is the circumferential stress that's calculated from the CEPA equation. All right. And the CEPA equation, I didn't include that here because you know, it's a well-known equation. So to the interest of time, I'm not going to talk about the CEPA equation itself because you can find it in those articles and references that was on my second slide. So what I want to talk about now are the future improvements that we are planning to make in the model. One of the improvements is to account for the lateral soil pressure when we do the overburden soil calculations. So in the existing model, the soil overburden is simply unit weight times H, all right? So one idea, and this is very conservative, and sometimes it becomes a bit unrealistic. It's just too conservative. One way to handle it, to make it a bit more realistic, is to account for the lateral pressure. And why that's important? Because if in reality you do have that lateral pressure on the pipe, which is shown by K naught times gamma H. And K naught is a coefficient. It's known as the coefficient of lateral soil pressure or static soil pressure. So that coefficient can help because if you think about it, this component K naught times gamma times H, and K naught is usually less than 1 in this type of calculations. This component actually acts like a hydrostatic test pressure, right? So it's like you have a pipe at some depth, and this component K naught gamma H, it acts in all directions around the pipe, right? So your overburden pressure, when you account for that, your overburden pressure is decreased by this amount. Because this pressure, the way it affects the pipe is like a hydrostatic pressure, like the internal pressure of the pipe. And the stress that it creates in the pipe is much less compared to the CEPA stress. So this is one of the improvements that we are considering to make in the model, which allows the user that if the user knows a good value for K naught, it allows the user to take advantage of that and decrease the overburden, the effect of the overburden pressure on the pipe. And another thing is basically the angle of the crossing. So as I said before, the angle of the crossing typically assumed to be 90 degrees. But in the new improvements, and if you use the load matrix option, there is a way you can actually perform your analysis with different angles. But then you have to go through the trouble of rotating your load matrix. Okay, so in the new improved model, what we are considering is to do it automatically, to allow the user to basically introduce a crossing angle. And by doing that, if your crossing is 90 degree, you enter 90 degree, right? If it's something else, you can do that. And that is going to include a parallel configuration where you have a vehicle that actually runs along the pipeline, either over the pipe or at some offset distance from the pipe. Something like that is going to be useful when you have a pipeline that is either under a road or is parallel to the load on the road on the shoulder, in the shoulder. When there is a minimum offset that is always maintained. So those are, that's another improvement. And here I have explained that in more detail, that you have a vehicle with some offset distance that is basically running or operating near the pipe. And that offset distance could be any value, including 0, right? And then another improvement that we are considering is to, when you use the load matrix option in the current CEPA model, you need to tell the program where the vehicle is located. There is an XY coordinate that you put input to basically to tell the program which location of your load matrix is your critical point. And you probably, if you have used that, you probably know what I'm talking about. In the new version, we are actually going to optimize the load matrix automatically. When you use the load matrix option, it's going to calculate the critical point automatically. So you don't need to know it or guess it up front. Then another improvement is to include timber mat or concrete slab, or basically any type of slab. This is going to be another improvement that we are considering in the CEPA model. So when you run your analysis, if it fails, then it allows you to repeat the analysis with a timber mat or a slab over the pipe. Just to show you, what's going on visually, I have an example here, which I have solved. This is still a spreadsheet. This is not implemented, but it's something that we can implement fairly quickly into this technical toolboxes. So here we have a bulldozer, and the graph that you see here is basically the footprint of the bulldozer, right? These are the tracks of the bulldozer, these blue stuff over here. And actually each blue circle is a point load. So this is how I defined my load matrix. All right. I also use the impact factor of 1.5 in this analysis. So all the loads, the bulldozer is 60,000 pounds, but all the loads are increased by 1.5 times to account for dynamic impacts. Here are the other inputs that I have. It's a 24-inch pipe. You see there are 3 columns. I'm going to explain the difference between them in a minute. But in all cases, the pipe is 24-inch diameter, wall thickness is 1/4 inch. It's grade B. The maximum internal pressure of the pipe is 525 psig, and the minimum pressure that I assumed is like 20 psi, right? And the other parameters which I have here is the type of seam weld. Then over here I have the Young's modulus of the material. So for example, if this was an aluminum pipe, I could have changed these values to make it aluminum, which is the modulus and Poisson ratio. Over here I have the thermal load on the pipe. It's plus minus 36 degrees differential temperature. Cover depth is 3 feet. So I did the analysis for 2 different scenarios here. I used the prism load, which accounts for 100% of the overburden. And then I used the option that I talked to you, explained with K naught, which reduces the load on the pipe, the overburden load. So here, the K naught value that I entered is 0.43. Right, which means that it's gonna decrease the load by some percentage, almost by 50%. The other stuff that I have here is just the soil properties, which is mainly used to calculate the Winkel spring coefficient of the soil for the beam on elastic foundation calculations. Then over here I have my E prime value. Again, it's 1000. The bedding angle is 60 degrees, and the spring constant, when I enter 0 in my spreadsheet, it uses the information that are provided here to automatically calculate that. All right. And then the last thing here is that the first analysis is a 90-degree. The second analysis is a parallel situation where the pipeline makes a 0 angle when the vehicle makes 0 angle with the pipe. All right. And here it can be at any offset distance. So it calculates the offset distance automatically in such a way to make the stresses maximum. All right. And then the last one is fixed angle crossing at 90 degrees. But the difference between the last case and the first case is the prism load versus prism load with K naught. And here, if you look at the results, you will see that first of all, using a parallel the difference between these two is the angle of the crossing. The first one is a typical 90 degree. The second one is a parallel configuration. And you see that the stresses are slightly higher when the vehicle runs parallel to the pipe. Like for example, the maximum longitudinal. Usually it's the maximum longitudinal stress that gets affected the most by the angle of the crossing. So that's what we see here. And then in the last one, I used that K naught idea. And the first two, actually, they failed because my equivalent stress exceeds 90%. but then you see that the last one passes, right? So it does make some difference here, right? And then on the first one that failed, I repeated the analysis with a timber mat. Here I have entered the characteristics of my timber mat. It's 10-inch long. The timbers are 8 by 8, and here also we have elastic modulus for the timbers. So here are the analysis results. Increase in equivalent stress with the timber mat, it's 84%, whereas without that it was 91.9. And with that, my presentation ends. I think we still have a couple of questions that we can answer, and also I think there is some questions for the audience.
Yep.
Go
so
ahead.
Where we go from here, again, we're kind of looking at ways as technical toolboxes of how we can enhance our own CEPA model within our surface loading analysis software. So if you could, we're going to put up 3 poll questions. If you all could just answer those today, just because this is going to help us guide, how much should we prioritize getting some of these enhancements in our software versus not. So we'll put up each question for about 20 seconds and then move on to the Q&A. We do have quite a few questions. I think since we stopped for Q&A the first time, we've had over 25 questions come in. So I'm glad you all are engaged, and we'll get as many as we can today, and then the rest, hopefully we can answer via email.
So as far as the remaining questions go, do you want me to continue addressing them?
Yeah, so we're on
all right.
question 2 of 3, and then so probably about half a minute more of our poll question.
Sure.
And then we can do the lightning round on the remaining questions around CEPA. So, okay, and the last question here. Very good. Okay, so Dr. Zand, I'll go ahead and start with the question list from where we stopped before. As I mentioned,
go ahead.
There's probably close to 30 additional questions in there now, so we're gonna.
Yep, I can see that.
Well, we'll get as many as we can, and maybe go slightly over for folks, and then hopefully answer the rest via email. Okay, so you mentioned the CEPA model calculates fatigue. Do we still need to compare to the fatigue endurance limits in 1102?
Yes, yeah, that's what it does. It basically calculates the live stress and compares that against 1102 limits.
Okay. Can CEPA be used for HDPE pipes?
So the short answer is it can, but the version that's available on Technical Toolboxes, that is fine-tuned for steel pipe or ductile pipe. I don't recommend using it for HDPE. There are other methods, and I even think Technical Toolboxes might have another module for plastic pipe. So I would not use the CEPA module that's in Technical Toolboxes for plastic pipe.
Okay. How does the CEPA model factor in cyclic fatigue?
All right, so that is the way it does is by using the limits that are in API 1102. There are limits known as the fatigue endurance limits in API 1102. And CEPA simply compares the stresses, the live stresses, from CEPA calculations against those limits.
Okay. Next, the CEPA calculator appears to have a lower limit for depth of cover before it does not calculate correctly. Why is this, and what is the lower limit? For example, a calculation on a 20-inch pipe may fail at 1 foot of cover, but pass at 1 inch of cover.
So yes, it does. The main reason for that, well, there are two reasons. One reason is that the CEPA model has not been tested against actual experimental data for cover depths less than about 2.5 inches, right? So one of them is that we don't have any data to argue that the CEPA predictions are acceptable when your cover depth is very shallow. But aside from that, some of the CEPA assumptions they get violated when your cover depth is too shallow. So like for example, the Buzinesky equation, if you have a object like a pipe with only few inches of cover depth, then we can't use Buzinesky equation. All right, there is a question that I think you skipped, but that's again about plastic pipe, so no problem. Let's go to the next one.
And I will answer that one. So we do have some crossing calculations in Pipeline Toolbox for polyethylene pipe, but that's not for the CEPA model. So we can talk more about that offline.
Great.
Okay, next question. Can you elaborate more on how the through thickness bending stress due to ovalization translates into a longitudinal stress? The equations use Poisson ratio, but is this appropriate for a bending stress with it not being a uniform membrane stress?
It's an approximation, but yes, it's roughly acceptable because it's basically the way we look at the longitudinal direction of the pipe. It's restrained, so it's almost like a plane strain situation where you can calculate your longitudinal stress by multiplying the circumferential stress by the Poisson's ratio. Now, we use a couple of assumptions here. For example, we are assuming that the stresses are linear elastic, but that's a reasonable assumption until the pipeline starts to yield. Yes, but if you want to do anything more accurate than that, you have to use finite element analysis. Unfortunately, there is no other analytical model that can give you better results.
Okay. Is agricultural equipment any concern in terms of surface loadings?
Yeah, they do. They do for a couple of reasons, because they are heavy, right? And they are getting heavier and heavier. I mean, new equipment, they're just heavier than traditional ones. That's one concern. Another concern is that the cover depth. In an agricultural field, your cover depth can change. So it could be less than what you think it is in reality. And it's not paved, so that's another thing. You can get soil erosion or other factors. Now, one good thing is those equipment usually have a low tire pressure, which tends to distribute the load over a larger area, and that is going to help.
Okay. Previously in the PTT surface loading tool, entering a reasonable or actual trench width yields an unreasonable conservative combined stress. In the training, we were instructed to use a trench width equal to the diameter of the pipe to yield more reasonable results. Has this been addressed in these enhancements?
So in the new tool, when you use CEPA, the trench width does not enter. When you're using the prism load, the prism load is independent of the trench width. Now, there is a question where you should use the Marston model that accounts for the trench width versus the prism load or prism load with K naught. But that's a different question. Basically, if you have a rigid pipe like a concrete pipe, then Marston model is probably better than the prism load. When you have a flexible pipe, prism load should be conservative. So basically, again, short answer to your question is, if you use prism load, you don't have to worry about it.
Okay. How other sources of pressure can be included in the CEPA calculations, and in which form?
I'm not sure I understand the question. What other sources of pressure? Or do you mean outside force?
Maybe
So
we can skip that one.
you know, the CEPA model does not include any load other than those that I mentioned.
Okay.
Right.
Without pipe installation information, do you have any guidance on what to use for soil bedding angle? Is it accurate to assume a larger bedding angle over a longer period of time? And if so, do you have any rules of thumb?
Well, the rule of thumb that some pipeline companies use is that if the pipeline is a vintage pipe, has been sitting there for 10 years or more, they can use a bit higher bedding angle. A typical bedding angle, which is conservative when you have no information, is 30 degrees. Now, if the pipeline has been sitting there for like a decade or so, maybe you can use a little bit higher, but I don't have any experimental data to confirm that. It's mainly based on you know, engineering judgment and intuitions.
Okay, general question, how much conservatism is built into the CEPA model?
A lot. CEPA model generally is very conservative. So you do have again, only on the surface loading part. The safety factor or the calculated stresses are 2 to 3 times bigger than the actual stress. It doesn't mean that the calculated equivalent stress is 3 times bigger. No, because the CEPA, the surface loading induced stress, is only a part of your total stresses, right? So you have the overburden pressure from the soil, you have stress from operating stress from thermal expansion of the pipe, from internal pressure. So all those stresses, they are calculated fairly realistically. The only stress where you have some level of overestimation is the live stress. But then there are lots of variabilities, which, you know, could be a cause for concern. Like what's your actual E prime value, or what's your actual bedding angle? We don't really know those things with a high level of confidence. So we have to be a little bit conservative here. Even if you use finite element and similar methods, if you use similar assumptions for the bedding angle and your E prime value, you get results similar to CEPA, right? So mainly the conservatism is your input values, not the model itself. All right.
Okay. Many times we've been asked to analyze existing pipe with little cover and design wooden, concrete, asphalt, or gravel pads and additional cover to ensure pipe stresses don't exceed maximums. Does the new analysis help us determine various cover situations?
So, I mean, the cover situation, it's simple. You can always increase, you can start with your existing cover depth, and then you can manually increase that. Because it's easy, I don't see a good reason to, you know, make it automatic. You can always increase your cover depth until you get desirable results. On the other hand, if you want to use timber mat and things like that, yes, the new improvements will help.
And I would also add here, within Pipeline Toolbox, we do have a new advanced calculation called sensitivity analysis that does kind of help us here, and it helps us look at these various scenarios just with one run of calculations. So we can provide more information there if needed. Okay, I know we are about at time. Dr. Zand, are you okay if we go maybe 5 minutes over? Just to try and get
Let's go. Let's continue.
I'm going to skip around to a couple of the ones that I think are relevant for everybody. Is it the right assumption that the CEPA equation is recognized by the ASME and CSA standards?
I don't know. I know the CEPA equation is recognized in Canada by CSA, but also I know that recently I think they removed the CEPA calculator from their website. But the model that they have adopted, I believe, is similar. With ASME, I don't know. I'm not sure that it has been adopted, but it's something that many pipeline companies actually use. So it's a de facto, whether whether it is in the standard or not. But I haven't seen that in ASME standards.
Okay. Will the model still enable assessment of parallel but offset scenarios?
Yes. Yeah, it
Yep.
does. I mean, the new improvements will allow you to have a parallel but with some offset. Yeah.
Okay. How sensitive to the results is the crossing angle you described? Is it the same for lateral soil pressure?
The crossing angle is usually not you um, a long vehicle. But the thing is, if you do it with 0 angle instead of 90 angle, you can actually get few percent. Your stress might be few percent higher, right? So it's important if you're close to your limit. If you do your analysis with 90-degree assumption and you have a good margin before you hit your allowable limit, then probably you don't have to repeat it with 0 degrees. But if you are at, like the example that I have, I had, if you are at 85%, then it could be a problem if your actual angle is not accounted in the analysis. Also, same is true if your vehicle is very long, like a train or one of those trucks with like 100 wheels, things like that.
Okay. Any plans to include compaction roller equipment that utilizes vibratory compaction within the drums?
It is possible to analyze it even with the existing tool that you have. So if you have a vibratory equipment which is going to cross the pipeline with vibration on, all you need to do is to add the centrifugal load to your drum weight. Okay, and then when you add the centrifugal load, because you have accounted for the dynamic effects, you can use an impact factor of 1 or something very close to 1. So yes, you can do it with even with the existing tool. But there is also another aspect. When you have vibration near the pipe, it's also recommended to do a vibration assessment in addition to the surface loading, which is different than surface loading.
Okay. For the parallel vehicle configuration with an offset of 0, does that center in the vehicle directly over the pipeline? And will we be able to simulate a load directly over the pipe rather than centered over the pipe? Or in other words, are we able to simulate the tires running directly over the pipe?
Yes, actually you can do both. If there is a clearance between the pipe and your wheel path, you can fix your offset distance. Okay, so you can run a parallel scenario and you fix your offset distance, and that way the center of the vehicle and the pipeline will actually have that minimum offset that you have introduced, right? So let's say you have a vehicle that is roughly 6 feet wide, okay, and you want that vehicle, the wheel path of the vehicle, to maintain a 3 feet clearance with the center of the pipe. Okay, so if you put the center of the pipe, your vehicle at the offset distance of 6 feet, that way your wheels keep an offset of 3 feet to the pipe. Okay, so the point is it's up to you to define your geometry the way you want. But if you do it right, yes, it can do that. And on the other hand, if you want your vehicle or your wheels to cross the pipeline, you can still do that. And there are 2 ways you can do it. You can do the parallel configuration and set your offset distance to the right value. In my example, that's going to be 3 feet, because when you put the center of your vehicle at 3 feet, then the wheel is going to be over the pipe. Okay. Another option is to just set the angle to 0 and let the program move the vehicle to find your critical point, if you are not sure what is your critical point. So yeah, all that are possible. Yep.
Okay. Do you have any examples of the stress results of a perpendicular versus a parallel crossing?
Yeah, I had the example that I shared did exactly that. So there was few % difference in the stresses.
Okay, is there a lifespan calculation of the newly introduced timber component to the calculation?
What span? Lifespan?
Lifespan?
Let me see, where's the question? I kind of lost track. Not sure I understand the question.
Okay, let's go 4 more minutes. Again, we have so many questions. We'll just try and stick to the ones we have time for. The next question I can answer. So it's, can the model prescribe or calculate a minimum thickness for steel plates or timber mats to achieve a designated load limit? Cindy, this kind of goes back to my comment around, we have this new sensitivity analysis module that's added into our surface loading calculations. That would kind of provide that for you there.
Sorry, I thought you were going to answer that question. Then was it for me or you?
It was for you, Dr. Zand, but
sorry. So could you then repeat it?
It was a question of, can the model prescribe or calculate a minimum thickness for steel plates or timber mats to achieve a designated load limit?
Not directly. The way it works is that you need to enter the properties that you want and let the program give you, calculate the stresses in the pipe. And if they are not acceptable, you should increase the thickness until it's acceptable. So there are a couple of factors that help. It's not just the thickness of the plate. The length of the plate or timber mat also plays an important role. So you can increase either the length or the thickness until you get desirable results.
Okay, is there any assumption or drop-down list for the K0 lateral soil pressure coefficient for different soil types?
Yes, there is a way you can calculate that. At this stage, my recommendation is to talk to your geotechnical people instead of using default values. But if you want to use like a default value, you can find some recommendations in soil mechanic books. For example, one idea is to say it's equal to 1 minus the sinus of the friction angle. That's for sands. So if you know the friction angle, or if you can estimate that, you can use that equation.
Okay, this will be the last question, just as I know we're 10 minutes over, and frankly, we could go for another half an hour here with the amount of questions we've gotten. So regarding cover and its effect, for the same soil type, if the pipe is newly installed, can it be assumed that the effect of the protection from cover would be different from if the pipe has been buried for over 40 years, as the soil may be much more stiff? And if so, can this be accounted for in the calculations?
Well, that's a bit tricky. The answer is yes. If you have consolidated soil, it provides more protection for the pipe. But there are a couple of things that you need to keep in mind when you make assumptions like that. The first thing is, if the soil gets compressed over time, your cover depth decreases. So if you start with a cover depth of 3 feet, if you're assuming that your soil gets more compacted and you want to take advantage of that, then the question is how much of cover depth you lost because of the consolidation of the soil, right? So you have to, include that in your calculations. Another thing to consider is when soil consolidates or gets more compact, you could get differential settlement under the pipe. Okay, so the pipe that used to be straight now might have some bends because of the soil consolidation. So again, the question is, did you account for that, or how you want to account for that? But let's say in an ideal situation, let's say you don't have any of those issues. Let's say your pipeline did not experience differential settlement. the soil got consolidated naturally, and you know your cover depth, your existing cover depth. You can use a higher E prime value and a higher bedding angle for your analysis.
Very good. Okay. Well, thank you all for the very many questions. Like I said, we'll try and go through the remaining ones we didn't get to and figure out how we can get some answers there. But would like to thank Dr. Zand for the really great presentation, and thank you all for the great interaction today. As I mentioned, you will get a copy of this presentation in the next 48 hours. And if you have additional questions, you can reach out to us here at Technical Toolboxes. So thank you all again, and have a great day.
Thank you.